Today we have Surya coming from MIT to talk about her latest work, which is universal SNARGs for NP from proofs of completeness. Take it away.
Hi, everyone. Today I'm talking about universal SNARGs for NP from proofs of completeness. This is based on joint work with Chenjong, Yael, and Alex. And yeah, I would like to thank Chenjong for many of these slides. They're pretty awesome. And yeah, feel free to stop me at any point if anything is unclear. So I decided maybe I'll first start with a TLDR slide for the people who are familiar with all the words in this slide. So the first main result is that we built a non-adaptive SNARG, which is universal, in the sense that I'm giving you an explicit construction, which is sound as long as one of the following things exist. A so-called natural SNARG for NP. So if a SNARG exists, then our SNARG is sound. Any natural designated verifier SNARG. So even if there's a secret key SNARG, our SNARG is sound. And in fact, any natural witness encryption for NP is also sufficient. So what am I saying when I say natural here? This is just a word I coined for the purpose of this talk. So when I say natural, think of it as a proof system, which has a propositional proof of completeness. So that means you can write down in mathematical logic a proof of completeness for the system. And here's the second part of the TLDR of things that are not covered in this talk. So we also have results in the adaptive setting. So assuming LWE, we built a publicly verifiable adaptive SNARG given a designated verifier adaptive SNARG. So in this setting, we couldn't get something universal, but we can at least boost a secret key to public key SNARG. And so as a corollary of this, combined with one of my earlier works, you actually get that you get adaptive publicly verifiable SNARG from any natural witness PRS. So it can, I'm not defining what this is, but it's like an extension of witness encryption. So you can build witness PRS from IO and 1A function, or you can also build witness PR from UP for evasive LWE from my previous work. So this is a slightly different modular construction from water smooth. So this adds on to the many, many constructions we now have of adaptively sound SNARGs. Okay, so I will not be talking about this again in the rest of this talk.
Sorry, question about like slide 1, which is not the title slide. So natural. So I want to understand like proof of completeness of what? That like the cryptographic.
This is a TLDR slide. I will. Okay. Yeah, I will define this more later.
And maybe also a quick question for the witness encryption scheme. There's this candidate based on like generic auto groups. Is that one also natural?
I have not checked.
Okay.
But if you can write down the proof for me with just commutativity, associativity, basic arithmetic, then it probably does.
Thanks.
I'll also explain what probably does have proof of completeness. Okay, so what's a SNARG? So a SNARG is a succinct non-interactive argument, right? And there's a prover and a verifier who share a common reference string. And the prover now wants to prove this X is in the language. So to do that, what he can do is send over a proof which is much, much smaller than W, which is where the succinctness comes from, to the verifier. And if he does everything correctly, so that means for all X, the honestly generated proof from an honest W is accepted. And when I said completeness in the title slide, this was in fact the type of completeness that I'm talking about. I want a propositional proof of this fact of the SNARG. Okay, so soundness says that if you have a polynomial time cheating prover, for any X that's not in the language, an efficient prover should not be able to come up with a cheating proof. That's what soundness means. Any questions?
So we don't care about knowledge then?
No, this is not a SNARG talk. The disclaimer. Although I realized earlier that actually our construction is universal SNARG as well. Fun fact, but that's not the focus of this talk. Okay, so can we build SNARGs with a G for NP? So there's many works that try to do this, but many of them use either like a random oracle model assumption or knowledge type assumptions. So what can we do from standard falsifiable assumptions? So there's a very informal barrier here that I have to say, but it has been like circumvented in many different ways recently, but there's a general impossibility result that says that it's very difficult to come up with a reduction that runs in time less than 2 to the X or 2 to the W, 2 falsifiable assumptions. So this inherently makes it difficult to come up with short proofs, which has more than X or W. But again, this is just a very informal barrier that I'm stating here on why many works have found this problem really difficult. And there are many ways around it. But what do we know from standard assumptions? So assuming indistinguishability obfuscation, we have many candidate constructions for SNARG for NP. But if you want to use lower level assumptions like learning with errors, DDH, quadratic residuosity, and so on. We have bounded depth P or batch arguments, monotone policy and batch NP, and for some natural subclasses of NP intersect co-NP. And we're not quite at NP yet. So what can we fill in this blank? Can we construct SNARGs for NP from learning with error or any other related assumptions? So why do we want to do this? Why do we care about building SNARGs for NP from assumptions other than I? So here are a few reasons. The first thing is we want to diversify our assets. We always want to build crypto from many different assumptions. So this is just, we just wanted to now construct SNARGs from other assumptions. The second thing is in IO-based constructions, the common reference string is a structured program which has a secret in its head. So in particular, some trusted party who will end up knowing the secret will have it generate this CRS for us. So can we come up with a construction which is unstructured? And also you can ask, do we really need such a big hammer? Like IO has been somewhat crypto complete in the sense that it implies almost everything in cryptography. So do we really need the full power of IO to achieve SNARGs, or can we actually rely on something weaker? And also finally, there are no good post-quantum IO candidates with like a non-vacuous proof or non-ad hoc proof. So this is another reason why we care about this. Okay, so this leads us to our main result. First, our main result is that we construct a universal SNARG for NP. So we give an explicit construction. So I can like write down this construction for you right now. That is sound assuming learning with errors and the existence of any so-called natural two-round argument for the corresponding language. So what's a natural two-round argument? Okay, actually, I don't think that's the first thing I'm talking about. So, okay, so the soundness guarantee is non-adaptive. So that means you have to choose the X that you're cheating on before seeing the CRS. And the CRS is transparent, so it's not a structured program.
Just from IO, not right. Like,
I mean, you already have a SNARG from IO, so it's not. Like yes, okay, yeah, you're right. We don't know this from IO. It's transparent setup, we don't. The universal, then it's a not really meaningful question. So again, I want to stress this is universal, so that means you don't need to give me this two-round argument, and my construction is just secure as long as one exists. And if you're familiar with other universal constructions, ours is an 11-style construction that enumerates all possible constructions. So it really avoids this galactic inefficiency and is quite good in terms of efficiency compared to these style. If you're not sure what this means, don't worry about it. Okay, so what's a two-round argument system? So this picture, I drew it this way intentionally. So for example, a SNARG would imply such a system where the first message is the CRS and second message is just the SNARG proof. In particular, it's okay if this system is even a designated verifier SNARG. So the verifier could hold a secret key and this would still go through. In terms of witness encryption, will also imply such a two-round argument, and we'll see this later. And looking forward, we can build this from LWE and a base level. So what do I mean by natural? So by natural, I mean that you can prove the completeness of the two-round argument system in a propositional logic system called extended Frege. So what is this system? So a proof in the system looks like this. So every line is a Boolean formula. So it's either an axiom or it's an implication. So for example, you can take one previous lines and then come up with a tautology based on it. Or you can also define new variables in the system. And at the end of the day, if we can write down a bunch of lines of proofs so that the final theorem is the theorem statement that the final line is actually the theorem statement that you care about, then you have a proof of this in this propositional system. Yeah?
Can you say the inference again?
Yeah, inference here is just the one-size tautology. So you can like think of you can like brute force like the truth table of it. But the classic one to think about is modus ponens, right? X is true and X implies Y, then Y is true. So just think about modus ponens. I'm just saying one-size tautology here to like avoid those words, but yeah, modus ponens is like an axiom in propositional logic.
So I guess like thinking by example, so like a standard cryptography paper, let's say like the previous paper in the slide, with their proof of completeness in extended Frege logic system?
Yes, if the components did. Like for example, the previous work used FHE and BARGs.
Yeah. And
in this paper that will eventually appear on preprint, I proved FHE does have a proof of completeness. And BARG extended Frege, yes. And BARGs, I think you can just check case by case. I think the Waters BARG does. I haven't checked the more recent ones because I have to go into the correlation intractability.
Okay, like I guess,
but
what would I think, since it seems like it's kind of interesting here, like what would like a cryptographic primitive which has like some notion of completeness, like why would it not have an EF?
Okay, I'll get to that in a few slides.
Okay.
Yeah. But I want to first define what I mean by completeness property in EF.
Okay.
So that is something more concrete to look at. So what happens in this two message argument system? The first, the verifier sends over a message which takes as input X, which is the instance, and uses some randomness R to generate some query Q. Then the prover sends back some algorithm P of X of W of Q. So it takes X and a witness W for X and the query Q and output some proof pi. And then there's the second part of the verification algorithm, which checks whether it accepts or rejects. So what does it mean for this to have a completeness proof? So you want to be able to say something like this, right? For any X, W, and randomness, if W is a valid witness for X, so that means R of X, W equal 1, and Q is honestly generated. So that means there exists some randomness R and input and the instance X such that Q is equal to V1 of X of R. And pi is honestly generated. So that means pi is generated from X, W, and Q. Then pi is accepted by the verifier. Does this make sense? So this is how you would write in simple what the completeness property of the system would be.
So prover randomized here?
Here, no. I guess you can make it randomized if you want like zero knowledge, for example. Then you just have to add another R. But for this slide, I'm assuming it's deterministic. Okay, so going back to the theorem statement, I'm just saying that as long as there exists some two-run argument system with a polynomial-sized EF proof of completeness, then our SNARG is sound. So now, how valid is this assumption? This is exactly what you were asking earlier. And my belief, very informal belief, is that for most cryptographic systems, completeness is almost for free if it's already perfectly complete. So why do I say this? Because in many cases, we have a very simple mathematical proof of correctness. So for example, the next slide, I'll show an example of El-Gamal, but it only uses very basic properties of arithmetic. Like it uses plus minus and like maybe, distributivity or associativity, commutativity, and so on. So it uses very basic properties of arithmetic. And turns out, if this is all it uses, there's these amazing people who've already shown us how to come up with polynomial-sized EF proofs for these facts. So therefore, you can compose these proofs to come up with a full polynomial-sized proof of completeness for such a system. Yeah. So for example, if this is from Jane and Jin 22, Abhishin Jane. So for El-Gamal, all you need is like basic properties of arithmetic, as you can see here. So you just need like g to the f of r is equal to g to the r of s, and so on. So if this is all you're using, then you should probably have a proof. So maybe your witness encryption candidate only uses these kind of things, and then you could go.
But I mean, like LPM type of stuff, what happens to like secret and then you get a measure, you check it with smart.
Okay, so I'm not too familiar with LPN, but for LWE, for example, if you just sample from a Gaussian, there's a chance your noise is too big. Then you just throw, you can just change the scheme to like reject very, very like dense noise. You can't?
Like
then it doesn't. Then that actually doesn't. So, but that's not perfectly complete. That's why. But so what my claim on the previous slide was that if it's perfectly complete, it probably has a proof of completeness. But so again, it probably has a proof of completeness for free, but I'll give some caveats. You still have to verify this on a case-by-case basis. So for example, if the correctness of the scheme relies on some computational assumption or some de-randomization assumption, then you probably can't hope to have a proof of completeness. Why? Because you need to prove the de-randomization assumption first to be able to prove the correctness of the theorem, but this is an assumption for a reason. And there's also impossibilities due to the so-called witnessing theorem. So as I won't describe exactly what it is, but I'll give an example of what it says. So assuming factoring is hard, you can't prove that AKS primality testing has a polynomial-sized EF. So you can prove that it probably doesn't have a polynomial-sized EF. Okay, that's the bad news, but here's the good news. So turns out it does exist for many things. So for example, it exists for Iridiner's PCP theorem. And in this work and in the prior works, they've shown that DG and punctuable PRS, Merkle trees, LW-based FHE, and other things also have PV proofs of EF proofs of correctness. And another cool theorem we were able to prove is that you can take any sub-exponential IO scheme and additionally assume sub-exponential LWB and come up with a natural IO scheme. And the basic idea for this is to like do IO bootstrapping and use that to cleanse an IO scheme to be natural.
So why do we need sub-exponential here?
Because you're doing IO bootstrapping.
Okay.
And that requires like essentially you take an IO scheme on and then brute force check that it's correct. That's the 2 to the n time algorithm.
Okay.
And then you put it through bootstrapping. So yeah, you need sub-exponential security because that algorithm is very slow. Yeah, did you have a question?
I guess I'm just trying to have some intuition here. Like, why is this AKS primality testing not provable? Like,
Yeah,
you have an algorithm, it's deterministic, it's polynomial.
Yeah, it's not provable in extended Frege.
Okay.
You can maybe prove it as EFC or something, but the idea is that so this is just a very informal barrier. But the witnessing theorem says that you can't have like a uniform proof of correctness for an algorithm where you can't also witness it. So in the primality testing, this would imply that if you can prove the correctness of it, you can witness the correctness of this. So that means if X is not a prime, it will find you a witness, which is a factor of the number. So assuming factoring is hard, then you shouldn't be able to prove with a uniform polynomial-size EF. That is correct. It's a very subtle point. Another example, think about is pigeonhole principle, because if you can prove pigeonhole principle, then you can find collisions. So assuming collision-resistant hash functions exist, you can't prove pigeonhole principle in EF. Does this intuition make sense? It just basically, it's a very constructive type of proof strategy, and it ends up witnessing things that it can also prove.
So is there like an alternative formulation of EF in terms of like, it's just like something a Turing machine can check or something?
Yes. So it's called PV, but I didn't want to go into it in this talk. So the uniform version of EF is called PV, Cook's theory PV. I think it stands for polynomially verifiable. So what I said right now is actually about PV, not really about EF. But it gives a barrier to constructing EF proofs.
Right. And EF, like PV necessarily is in EF, so it's the barrier.
Yeah.
For you.
Yeah. Yeah.
So I'm not very familiar with the proof system. What's the motivation? Why would I say?
Like what motivation for the context of this work, or
just for this kind of so
yeah.
Why is like qualified a frag proof or something? Is it like constructor logic or something? Like you said it like if you have a frag proof for PN.
Yeah, then you can I mean, this is just something proof complexity theorists introduced, and it ends up being useful for us. And this is just one possible like proof system that you can use, right? There's also VFC, for example. And for at least this work, we don't know how to use things like VFC. And the nice thing about extended Frege system is that each line is a circuit. It's like a Boolean formula. And that ends up playing very nicely with our construction. So that's why we're looking at this particular proof system. And what I'm saying here is that it actually captures a lot of things that we already care about. Does that make sense? And this is definitely the most
what about the algebraic kind of PCPs?
Algebraic.
Like not linears, but the original.
Does it have perfect completeness?
Check.
Okay, so this paper actually proves something even better. It actually proves the soundness of PCP theorem in extended Frege, which we don't even need. Right? All I need is PV proof of completeness. And I think that should be easy to achieve if it already has perfect completeness and it's all algebraic. Yeah? I mean, GKR should have one, for example. Like some tech protocols should have one. So going back here, this was our main theorem. I wanted to say a few things about related prior works that also use propositional proofs of for their constructions. So the work of Mathialagan and Jin constructs SNARGs from IO with a short CRF. CRS for languages which have an EF proof of non-membership. So what does this mean? It means that for all X not in the language, there is a proof that it's not in the language. It's a polynomial-size proof that there's no W that satisfies the relation. And similarly, in a previous work, which is very relevant to us, in JKLV, so this is by Jin, Kala, Lombardi, by Kudanathan, they built SNARGs from LW for the same set of languages, assuming that they have an EF proof of non-membership again. And the thing I really want to point out here is that these were kind of stuck in NP and psycho-NP, and our work pushes this fully to all languages in NP. So that's the main conceptual contribution of this work. Okay, so what are some implications of this result? So the first thing is that we can think of this as a best possible SNARG. So assuming LW in the existence of any SNARG, our SNARG is sound. So in particular, if you want to break our SNARG, you first have to break every natural SNARG. So that sounds pretty hard. Maybe it's easy to break LW at this point. So yeah, so it's really a best possible SNARG. And I guess I added the slide at the very last second because I realized it preserves knowledge soundness. So it's also a universal SNARG with a K.
What does it mean by the adversary needs to break SNARG? It means like
every SNARG. So basically, if you give me a candidate SNARG, and there's an adversary that breaks my SNARG, I can use it to break your SNARG. Does that make sense?
Like, no matter what your SNARG are. So the idea is like, their thing is secure if there just exists something secure. And I think that
the problem is just that, like, what does it mean by breaking natural SNARG? Like breaking in terms of like which property?
Violate
soundness. I can break the soundness of any SNARG. If you give me a candidate, and I have someone that breaks my SNARG, then I'll also break your SNARG if it has a proof of completeness. Yeah? Good question. And in particular, because of the transparency property, what you can get, assuming IO, is that assuming IO and LWE, there exists a SNARG for any NP language with transparent setup. And again, because of our previous theorem that you can upgrade IO to always be natural, EF proofs do not appear in this theorem.
So why do you need IO here?
I'm just saying it's one corollary of our result. That we know how to build SNARGs for NP from IO. So by plugging in that SNARG into this construction, you get this corollary. You don't need IO. I'm just saying it's a corollary of our result.
That's cool.
And before this, we didn't know how to construct transparent SNARGs, even assuming IO.
So if we had IO, would this potentially be a more efficient SNARG than the IO construction?
No,
okay.
Probably not. It's at least as inefficient, right?
Okay.
Because it looks like you put the IO in.
I see.
But the cool thing is you don't need the explicit IO. It's universal over all the IO schemes.
So you still need parameters like how
you need to know how long it is, how long it takes, and so on. So when I say universal here, I'm implicitly saying, assuming parameters A, B, C, I'll construct something using those parameters.
Okay.
Yeah. Okay. So going back to our checklist, we diversified our assets.
So maybe since you're just maybe don't talk about the results. So like say if you're looking at SNARGs for NP, like what is left? Like in terms of like the kind of questions. Like I guess
that was still using IO, and I still have two more things on this checklist.
Oh, okay.
Yeah. So first of all, we did diversify our assets because we constructed a universal SNARG. And secondly, we now have a SNARG for NP with a unstructured CRS. So we no longer need a trusted party. We can even use like an MPC protocol to come up with a truly random string for this SNARG to go through. Yeah. Okay. So we still have two things left in this list. So beyond universality, first of all, our SNARG boosts private verification to public verification. So that means assuming there exists any natural designated verifier SNARG, our SNARG is publicly verifiable and sound. And this is pretty cool because no such thing was known before. We always used to think that privately verifiable and publicly verifiable SNARGs are very different. And another cool thing, and so this first of all presents a slightly simpler target to build SNARG. So now you can just fully stick to the designated verifier setting. So as long as you have a proof of completeness, you're good to go. And one cool thing about this proof is that it actually doesn't require the reusability of the designated verifier SNARG. So in general, like this is something that's actually hard to prove. Like the original KRR algorithm, for example, was not reusable. This is saying that reusability actually doesn't quite matter as long as it's natural. Okay, so that's one implication. And where's my, okay. So another implication is that you can actually get SNARGs for NP from witness encryption. So what's a witness encryption scheme, if you're not familiar with it? So basically, in a witness encryption scheme, you first send over a encryption of a message M for an instance X, and a prover should be able to only decode it if X is in the language. Otherwise, M remains thin. So this gives you a two-round argument system because you can, if he decrypts, then you have completeness, and if X is not in the language, then M is hidden. So this is a two-round argument system. Does that make sense? Yeah, and this is pretty cool because we believe that witness encryption is much weaker than I/O. And in fact, we have witness encryption constructions from this assumption known as evasive LWE, from the works of Sabario and Vaikunanathan and V and Wicks. And there's also like new works that are really focusing on how to use witness encryption in place of I/O to build things. Like for example, there's adaptive ADE from witness encryption and how to use witness encryption to build things. So yeah, so we can see this work as fitting into this line of work that's trying to replace things, I/O with witness encryption in different applications. So here we do need this natural property of witness encryption, but modulo that, this is still a pretty cool implication. So as I alluded to earlier, in particular, this gives a SNARG for NP construction from lattices. So assuming LWE and evasive LWE, we have a SNARG for NP with transparency errors and non-adaptive soundness. So a few comments here. The best thing,
Doesn't evasive LWE imply LWE?
not quite. You need LWE to do anything with evasive LWE. Like the way it's written, you need to be able to prove things for the if condition with LWE. So you sort of have to say both things. Okay. So one thing I want to say here is that the best thing we knew from evasive LWE before this work was a SNARG for UP, which is a subclass of NP. So this work really shows that like this beyond universality aspect of it helps you like go further. So I'm not entirely happy with the state of affairs of just evasive LWE. Hopefully this is just a weakening of the target here for people to like try to come up with construction. So going back to our checklist.
Do you use private coin?
We do, but the yes, private coin, but this upcoming work uses public coin to construct witness encryption. But like the work that is about to appear in ePrint, it uses public coin, and you can use it to construct witness encryption. Public coin, yeah. But the construction in this paper, as of right now, is private coin. And fun fact, it does the original construction of VWW doesn't have a EF proof of completeness because it's not perfectly correct. So I actually come up with a different construction. But anyway, so now we've weakened the problem. We're saying, well, okay, we don't need I/O, we just need witness encryption. So we don't need the biggest hammer. We just only need a big hammer. Well, in terms of post-quantum I/O candidates, we give one from we now give a construction from evasive LWE, which is something, but hopefully we can do better.
Like the work candidate bio. So wait, how does this no post-quantum?
No, I'm just saying the goal was to construct a post-quantum SNARG for NP.
Oh, okay.
I'm now giving you one example from evasive LWE.
Okay.
Okay, back to the TLDR. Non-adaptive SNARG, assuming SNARG for NP, designated verifier SNARG for NP, or witness encryption for NP. So in particular for evasive LWE. This is a summary of the intro, and now I'll go into the technical details of this construction. Any questions at this point? So filling in this picture, yeah, now we now have a bridge between the two sides of this, which is we now have a SNARG for NP from witness encryption or designated verifier SNARGs and LWE and evasive LWE. Okay, I guess a little bit of a philosophical tangent here. Do you really need EF proof? Like ideally, like if we had an ultimate construction of SNARGs, do we really need EF proofs to appear here? And now I'm going to leave this question a bit open-ended, but maybe say a few words about this. Maybe logic is truly just a forgotten structure in cryptography. So for example, in a lot of cryptography, we use many objects in a non-black box way. Like for example, in like FHE, garbled circuits, and zero knowledge, and so on, we use the explicit circuits of these constructions. So maybe you can think of the use of logic as like the non-black box use of mathematical claims. So the work of J and Jin showed I/O for Turing machines via proofs of equivalence. So here they used a mathematical claim of the fact that M1 and M2 are equivalent Turing machines. And the work of JKLV constructed SNARGs for languages for languages for which there is a proof of non-membership. And in our work, we're using like the correctness and completeness claim of a cryptographic primitive. So the way you rule, yeah, again, I'm leaving this as an open problem. Do we need these non-black box techniques? And the way you would answer this in the right column is by showing black box separations. So it would be cool if you can do something like that on the left-hand side. But that's a cool open problem. Okay, so now I'll go into the technique.
Wait, so maybe now is a good time for my question.
Yeah.
About like what's left in SNARGs, what
Build it from LWE.
LWE.
Yeah.
Okay.
Like build a 2-round argument system from LWE. Build witness system from LWE. Anything. I'll be happy with anything.
Okay.
Yeah.
2-round private coin. No, that's not a thing. Okay.
Yeah. Okay, so what are our techniques? So the main thing we'll use today is called a BARG, a batch argument. So this is a SNARG for a special type of language, where basically every instance is really k instances, x1 through xk. And so now the prover has k witnesses, w1 through wk. And the succinctness requirement here is actually relatively minor compared to a usual SNARG setting. And here we only need that the proof size grows with one witness rather than being completely like independent of the witnesses. So the goal here is that you want the proof to be the size of one block rather than 3 blocks. So this will be our main tool for today. And the property we will use about BARGs is that you can somehow plant this trap door in the CRS in a undetectable way. And when you do that, you can extract the iStart witness that was used by the prover. Does this property make sense? So the guarantee is I can extract one witness of the k witnesses. And the prover should not be able to figure out which of the k instances is being extracted here. Yeah? So it gives like a very local soundness property. So yeah, and as a side note, you can actually generalize this to have be extractable on I different indices by just having I copies. Okay. So the first thing I'll mention is the hash and BARG construction that was introduced by CJJ and KBC. So the construction is actually very simple to state. So take the computation of the relation circuit. So let's say C is the relation circuit. Take the circuit computation of this. I'm just going to do exactly what the title says. I'm going to hash all the wire values. So I'm going to hash every single gate, every single wire value, and I'm going to BARG the following statements. So for all the statements correspond to the gates of this computation. So for every gate, I'm going to have one statement in this BARG proof. And the witness is going to be that I have a valid local opening to H to the wire values. So row L, row R, and row O are like the openings to left, right, and O. And I'm going to show you that the 3 values are consistent for the gate. Yeah, so the relation is basically checking whether the gate is satisfied and the openings are valid. Does this make sense? Does this construction make sense? Okay, so the thing is, we know how to prove this is sound, for example, for P, but we have no idea how to show that it's sound for NP, because the BARG guarantees that if you look at any like snapshot of any gate, you'll have a consistent you'll have consistent wire values, but that doesn't let you put together a full computation tableau because you can use a different witness each time. So you could have different wire assignments based on what witness you use. So we have no idea how to piece this together. So basically the problem is that we don't know how to show that local consistency of the circuit implies global consistency of the circuit. So this is a completely viable like candidate for SNARG for NP, but we have no idea how to prove this is secure. So the starting point is actually this new construction called the encrypt hash and BARG by the prior work by Jin, Kalai, Lombardi, and Mike Vindanathan. So it's basically the same as hash and BARG, except the CRS is also going to additionally contain an FHE ciphertext. That's the encrypted part. And this FHE ciphertext is just going to be an encryption of all zeros. Or you can also think of this as a random string for now. So now I'm going to take the relation circuit as before. But I'm also going to additionally take the circuit and add an extra circuit to it based on the FHE ciphertext. So I'm essentially extending the circuit, and I'm going to perform a computation on this extended circuit instead. So now there'll be a ciphertext that comes out of the extended circuit. There'll also be an out value of the original yellow circuit. And then now I'm going to hash and barg the full computation. So that means I'm going to write down the full circuit of the FHE eval function, and I'm going to hash and barg that full proof. Does this make sense? So all I've done so far is I've taken the original circuit and padded it to be bigger with the dummy FHE ciphertext, and I'm going to hash and barg this extended thing. Why is this helpful? Like, it should be completely unclear, and this is a very smart construction. And maybe just to say why this might be a little bit helpful is that it's kind of like error correcting. If I'm inconsistent somewhere, I must be inconsistent by padding the circuit, I must be inconsistent in more places. So you can hope that this padding actually buys you something, just to like foreshadow why this is helpful at all. And so the CRS, you should think of that the blue thing here is the CRS. So you can think of that as like a description of another circuit that you pad to this circuit. Right now, it's just an encryption of 0. In the proof, it will become a useful circuit. Yeah. So right now, it should make no sense whatsoever why this is helpful at all. But yeah, to foreshadow this, the proof will put an actual circuit. So now what you do is hash and barg this circuit. You send back out, which is a unencrypted value, a ciphertext PT, which is the encrypted value, and H imply, which is the hash and barg proof. And actually PT is not important here, but the verifier will accept as long as out is equal to 1 and the hash and barg accepts. Does construction make sense? Yeah, the construction is thankfully very simple to see, but the analysis is where things get hairy.
So ciphertext does nothing.
That's nothing here. I'm just putting it there so that you have something concrete to think about when I say FHE eval. But FHE, you can think of CT as being part of the hash value. Yeah, it's not important.
Okay.
I could have just written out H and pi.
So CT has a constant size then?
It's a size of one ciphertext, FHE ciphertext, like polynomial.
Okay.
Yeah. And out is 1 bit. And I guess technically you also have to show that out has a valid opening from H. I guess I forgot to say that, but yeah. Does the construction make sense?
Out has a valid
Yeah.
Okay.
Just to make sure that I'm not saying 1 and it's completely unrelated to the accepting hash and barg proof I gave you, right? So you just need an opening to make sure. Okay, the cool thing here is that the accept condition I've said here does not use the FHE secret key at all. So that's why this is publicly verifiable. The only thing that matters is that the hash and barg proof is accepted.
And CRS is essentially random. You don't have to pick FHE ciphertext.
Yeah, it's indistinguishable from random. So you could have said it was a random string.
Yeah.
Or that's just how all the FHE ciphertexts that we know from LWE look like.
Yeah.
So why is this sound? And yeah, as I said earlier, essentially what you're going to do is that you're going to replace this all zeros circuit to a special circuit E of X that we'll use in the soundness proof. And this circuit will end up using the 2-round argument system that I said earlier. Yeah. Okay. So now I'm going to give a very, very high level of what the JKLV proof of soundness looks like, but I'm not going to go into the detail. I'm just going to try to pick out the higher order bit of what this does. So recall that what they do is they show soundness in the case where it can prove that the relation circuit is unsatisfied. So suppose the soundness proof has size L, then essentially what we're going to do in the proof is that we're going to start from the 0 circuit and go to a special circuit that's built from the EF proof. And basically each line of the EF proof will correspond to a new hybrid. Okay, I'm not explaining at all how this works, and I have a bonus slide on that if people are interested. But this is the high level picture. There's going to be a hybrid per line of the proof. So the problem is that if you want to SNARG for NP, we don't expect all of NP to have a polynomial-size propositional proof. In fact, we can only hope for a 2 to the W size propositional proof because there exist hard languages. Yeah, and if you do that, then what happens is you'll have 2 to the W hybrids, And you need FHE security in these hybrids. So in particular, that means you have to set the FHE security parameter to be at least the size of the witness, so you won't gain anything. So that's why the previous work was really stuck at NP intersect co-NP. So here's our main idea. We want to shortcut the EF proof using cryptography. So first we do a few hybrids using, let's say, the completeness property of a cryptographic proof system. Then you do a hybrid that uses crypto. And then you go back to using, like for example here, we'll be using a soundness of the 2-round argument system. And then you go back to maybe using completeness. So you don't do the full proof. So you can think of this as sort of like a cryptographic proof of non-membership. The cryptographic proof that the relation circuit is unsatisfied. So that's like that main observation in this paper. So if there's anything I want people to remember from this talk, it's probably this slide. Okay.
Could you explain it?
So
what does it even mean by crypto?
So before I was only using like functionally equivalent things. I was only using like lines of the PV proof, like the EF proof. And if I'm only allowed to use that, then from the previous slide, like, I would need 2 to the W hybrids to say that to prove that the relation circuit R is not satisfiable, I would need 2 to the W hybrids, and I have not gained anything. But now what I'm going to say is instead is that the relation circuit is cryptographically unsatisfiable. That means I'm using a step where I'm using a cryptographic soundness instead of using an EF proof to show that those hybrids are indistinguishable instead of using the lines of the EF proof. That's the high level idea of what's happening. Maybe it'll be clearer when I show exactly what our proof looks like. But this is like the very, very, like if you're standing from like the moon and looking at the proof, that's what the proof does. Okay. Yeah, so one interpretation is that this is a cryptographic proof of the fact that the relation circuit is unsatisfiable. So again, this is the main result. I've said it enough times, so I'll skip this slide. So now, I guess in the soundness proof, I have to show you how I'm going to build this extension circuit. So before it was all zeros. So now I'm going to build a special circuit. So this circuit will take as input the wires of the relation circuit. And also W as input. So W is on this side, and the gates of the relation circuit are on the right-hand side. So the first thing I'm going to do is I'm going to hard code a circuit that computes the prover algorithm on a hard-coded input Q, a hard-coded query Q. Yeah. So again, I left the syntax of the 2-round argument system on the top right. And then now you'll get some pi out of it. And once you compute P and you have pi, now I'm going to run the verification circuit on it. So far it's actually exactly what you expected to do. And then I'm going to put an additional part on the side, which is basically the EF proof of completeness. So this is what it's going to look like under the hood of the FHE. Okay. So how am I going to argue soundness? The first, okay, this proof is not actually correct, but I hope at least gets across like the high level idea of the proof. So in the first hybrid, I'm going to use the fact that X is not in the language to say that if I use the BARG to extract out this proof pi, right? Because the BARG is extracting, so you can extract out the wire values corresponding to pi. You can,
pi is like succinct enough.
yeah, that's why we needed the 2-round argument system to have a small second message.
Yeah.
Yeah. So you can just extract pi. Then I can argue that if you extract pi, you better get something rejecting, or else you've broken the soundness of the underlying 2-round argument system.
So how do we know that the prover?
It doesn't matter. Like the prover circuit is in the FHE.
Yeah.
Whatever you extract there, it better be rejected. Because otherwise, I found a way to break your underlying 2-round argument system.
Okay.
Yeah?
Yeah.
Okay. So now I'm going to prove that if I run V2 on pi, the output here is V, right? And because V2 is a polynomial time algorithm, and you have all of pi, you can sort of like, I'll hand wave this, use like SNARG for P type techniques to argue that V here is equal to 0. Why? Because we know pi is rejecting. So if I run a deterministic computation V2 on pi, the output should be correct. So therefore the output is 0.
So I mean, like V2 is like necessarily like small space because the proof is
it doesn't need to be. The only thing that matters here is that the input pi is fully in the clear. So therefore you can argue like using SNARG,
Okay.
but don't worry about it.
Using like the hash opening. Using some. Okay, all right, I will.
Yeah. Okay, I didn't want to go into the details of this, so we can talk about it offline, yeah? But, okay, you can assume V2 is small without loss of generality, actually. So maybe that's easier. You can extract all of V2, and the output better be V equals 0. And then now, okay, so I've argued from one end, and now I'm going to argue from a different end that B is actually equal to 1. So now, the point is, what this proof is going to say this. It's going to say that if out equal 1, then B equal 1. Why? Because the completeness of the argument system says that if the relation circuit is satisfied, then verification accepts. So if you argue the other way, and I'm here hiding a lot of details from the prior work that uses EF proof, but it basically says that if out is equal to 1, then the EF proof lets you argue that B is equal. But now you have a contradiction, right? Because now you've kind of proven that, this inside circuit is unsatisfiable. Because if you argue from two ends, you get like B equals 0 and B equal 1. So this must mean that either the hash and BARG is not accepting or out is equal to 0. Does this make sense?
So
Feel free to ask me questions, yeah.
Yeah, so I guess no. So what's happening here?
Okay, I'm arguing that this
Yeah.
the hash and BARG cannot be accepted.
So
And the way
if
I'm
X is not in the language, then
Okay,
you're
excellent.
arguing that the hash bar cannot be accepting because
either if you argue from one end, you get B equals 0. If you argue from the other end, you get B equal 1, which is a contradiction. By assuming BARG security, you can prove both of these facts, just like contradiction. So that means the hash and BARG cannot be accepted.
because
It's very subtle. I can say that again. The
Yeah,
point
yeah.
is, okay, I can prove that B equal 1 using the hash and BARG soundness. I can also prove B equals 0 by the hash and BARG soundness.
yeah, if you can do that, like I believe you that
Yeah.
this can't happen, but I'm trying to understand why that's the case. So
Yeah, I mean, I didn't explain why the additional part works, for example, because that's just kind of black box from the previous work.
okay,
Yeah.
I mean, I'm
That's
not gonna
hard to
spend
get.
like another 2 minutes asking questions about this, but you might want to move forward.
Yeah, I think it's almost an hour, so let me finish this and then we
Yeah.
can talk offline. Okay, yay! But I've lied. This proof doesn't work because the EF proof is going to have the random coins used in the proof algorithm hardwired in it. So we have a problem here, right? Because now I can't actually use the soundness of the underlying proof algorithm if the same FHE encryption contains the randomness on the side. So this is actually not sound. So we need to fix this. So the high level idea to fix this is that the point is, we show the previous work kind of shows this theorem implicitly. If I have a sub-circuit that doesn't depend on the outside circuit and I do some computation with it, I can basically show that, okay, this is a bit too much, too wordy, let me see. Okay, I can basically say that if I extract the wire values out of the pink circuits, it should be independent of the outside of it. So even if the outside circuit contains, for example, the randomness used in the proof algorithm, if you only use the proof algorithm to compute the pi, it should not signal any information outside in the blue part. It's a high level idea. And how do we achieve this? Okay, so the moment you have this property, by the way, now you can argue that pi can only depend on P and should not depend on anything that's inside the EF proof. And yeah, this is achieved via using, okay, this is sort of achieved in JKLV in the prior work, but for a very different reason. And we realized that we can use that to kind of make this argument that the extended Frege proof doesn't leak any information. So the final construction, I like to call it encrypt square hash and BARG. Very proud of that name. So it's basically going to be the same construction, except I'm going to have 2 FHE encryptions instead of 1. Why does this help? It's going to be forever a mystery, but this is a pattern that has appeared in many works, even IO works, that you need 2 encryptions instead of 1 to be able to argue things.
It's like in the SNARGs would be.
Yeah, you have like multiple SSB hashes. Yeah, exactly. So now what you're going to give me, instead of just 1 encrypt hash and BARG, is you're going to give me 2 encrypt hashes and BARG. Oh, actually, no. I guess it's saying you do encrypt hash and BARG of 2 parallel computations and then hash it all at once. And this is good enough. And I guess because it's like time, I'm gonna skip this slide. But this just explains how you can prove local extraction property. But basically, the idea is in one circuit you have just the pink part, and the other circuit you have the pink and the blue part. And in the FHE1 soundness should hold because the blue part isn't there. And then you can prove that two parallel computations should give you the same value. Therefore, in the second ciphertext, you can still show that things are sound. Okay, I will skip this because I didn't talk about this, but yeah. So I'll summarize the results. So we constructed universal best possible SNARG for NP and a few implications for this. So first we have transparent SNARG for NP from IO. And we also showed how to boost any designated verifier SNARG to be publicly verifiable. And we also showed SNARG for NP from minus encryption and LWE. So in particular, this gives you a construction from a base of LWE and LWE. And finally, I guess I didn't talk about it, but we also show how to get adaptively sound SNARG for NP for witness PRS and LWE. So what are some open problems? So first, we've weakened the problem a lot in this work. So can we construct natural designated verifier SNARGs for NP from, let's say, LWE or any other assumption? Another question.
You need
two round arguments, yeah. A cool, interesting problem is that we were able to show witness encryption was sufficient in the non-adaptive case. Is it also sufficient in the adaptive case? That's a cool problem. And can we get SNARG from any designated verifier SNARG or witness encryption? Like basically without the proof complexity constraint. We were able to show this from the IO, for example. Can we show something similar for other primitives? And yeah, showing whether we need DCF proofs or showing that we don't need them. Either way, I'm very happy and excited to hear about. Okay, thank you. Feel free to ask more details now if you'd like, or any more philosophical questions.